All right, so in today's presentation, we're going to go over the Riemann sums for the double integral and how it looks like when you make it finer and finer. I mean, in other words, when you let that m and n go to infinity so that the sum of those thin boxes will approach the volume between the graph of the function and the xy plane, the domain, to be more precise. So if you use Maple, actually, the easiest thing is to go to to use these so-called tutors commands. Um, some of these packages that have this prefix student contain these so-called tutors, in which, the only difference between a regular command and the tutor command is that you have some sort of, as the name implies, some sort of demonstration of what you're getting. Approximate integration, it's basically another name for the Riemann sum. So let's, as always, choose functions that are very easy to visualize. So we're going to start with an inverted paraboloid, 15 minus x squared minus y squared. If you see it as a function in x and y, like z equals 15 minus x squared minus y squared, that's an inverted paraboloid. I mean, like in the sense that it's oriented downward toward the negative z-axis. But we're going to look just at the positive portion of it, so that that sits above the xy plane, and we're going to choose the portion of over the rectangle. So far we talked about double integrals over rectangles, and therefore we're going to stick to that. The domain here is minus 2, 2, minus 2, 2 for x and y. So once you hit enter here, then you're going to have already predefined the picture here with a Riemann sum. So let's start with smaller partition just to see how it's formed. Let's say you actually partition the interval into 3 equal pieces, each interval, which results actually in n squares. The midpoint upper, this is just the method of choosing the intermediate points. We're not going to get into that too much. Display, and then when you click close, you're going to see the whole picture rendered here in the worksheet. So first of all, let's look at the domain. Let's look at it from above. Okay, so as you can see, we clearly see how the partition is formed. Each side, the x side and the y side, is split into 3 equal pieces, resulting overall into 9 non-overlapping rectangles, or squares in this case. The definition doesn't care about the length of the division, so they could be actually rectangles. In other words, delta x doesn't have to be equal to delta y, but when we take the limit, that doesn't matter. So taking them to be equal just to look nice, that's not a problem. Here, the intermediate point is chosen according to a rule, like the midpoint rule, but it can be from anywhere each intermediate point can be chosen anywhere in each rectangle. So here we can see, hopefully everybody can see here, the little thin boxes. They're not that thin because there's not that many of them. And what's important is to understand exactly how each box approximates the region between the graph of the function and the domain. So the actual function is curved, right? Is this inverted paraboloid. If I look at one of these boxes in the margin here, you see a portion of it is above the graph, a portion of it is below. So there's some sort of error by addition or omission. The net effect of addition or omission, that's not easy to compute. It depends, of course, on the shape of the graph of the function. But the important thing is that going back to the tutor, the important thing is that if we make the partition finer and finer partition means that more and more, non-overlapping rectangles. So you make the partition by partitioning the segments into more equal pieces. So let's say I do now 8 by 8, which is basically 64 thin boxes. And you should already see, if I do that, how in fact adding the volumes of these thin boxes really approximates quite well the area between the graph of the function and the domain. You may still see some errors here. Let's now do a much bigger one. Let's say, let's say 30 by 30. That means 900 little squares. Takes a while. And now it's nearly, I mean, or you have to see it really close up to see the thin boxes. But now it's pretty clear that everything is going to converge to the volume of the region between the graph of the function and its domain. Okay. Complete analogy with calculus 1 version of it, except that in that case, that was an area. So as I said in the written part, this volume is with a positive sign if the region is above the domain, above the xy plane, and it was a negative sign if it's below. So let's choose an example when you have both. This is another paraboloid, but open up. And I choose the domain so that the negative portion of the paraboloid is also included. Obviously, the portion close to the to the vertex of the paraboloid is going to be below the xy plane because it's have this minus 10, right? So it's a paraboloid open up but shifted downward 10 units. And let's remain with this partition that is given here by default. And if you look at it from above, again, the partition is the same, right? I mean, it's 4 by 4, but let's rotate it and notice that when I plug in the intermediate points for the portion of the partition corresponding to the domain, which in turn corresponds to the negative portion of the paraboloid, the rectangles, excuse me, the boxes are below the xy plane. There's the 0 level here. So in the limit, you still add up the volume. You still add up the volume of the region between the graph of the function and the xy plane, but the portion below the xy plane is going to be it is going to have a negative contribution, in other words. So you don't really have the actual volume. That's the key thing. You have the volume, but with positive sign if it's above and negative sign if it's below. So again, let's make a finer partition here. Let's make, let's say 20 by 20. Let's see if it's easy to see. All right, so you still fill in the region between the graph of the function and the xy plane, except that the stuff below the xy plane is going to be with a negative sign. So if you truly want the volume, by the way, if you truly want to find the volume, you have to put an absolute value. Basically, you're taking basically in that case the double integral over the absolute value of the function itself, so that any negative contribution is still added to the overall volume. So I think that's it for this lesson, and I'll see you next time.